Hi everyone. In this lecture, we're going to be taking a look at atoms and molecules. Now, why are atoms and molecules important? Well, because they make up everything. So let's take a look at the beginnings of chemistry. To start with, periodic table. Everybody needs to familiarize yourself with the periodic table. The periodic table is the best cheat sheet you'll ever have for anything that has to do with chemistry. Hopefully in your chemistry courses you've learned how to take a look at this. But real quick, everything on the left hand side of the periodic table all the way up to this point right here, this little zigzag line, which is not printed on this particular periodic table, everything over here, these are all metals. On the right hand side, everything to the right of this zigzag line that my arrow is making right now, these are non-metals. And then things that are directly on that line we refer to as metalloids. So why do we care about the periodic table? Every one of the squares on the periodic table represents an element. An element is a pure substance. Okay, it is a substance that is the smallest that you can have of a particular substance and have it still be a substance. So these represent each of the different types of atoms that exist, as far as we know, that exist anywhere in the universe. But we know that this is what we have here on Earth. And it would be, it's not so much that we even think that you could have them in other places, have something else someplace else, because we know how these are put together. So we're going to be taking a look at all of the information that you can get from the periodic table. The fact that the periodic table tells us how many protons, neutrons, and electrons a typical atom of this particular element has. This gives us the symbol for the element. For instance, if we take this square that's right here, the symbol Cl is chlorine. If you notice, in all of the symbols in the periodic table, the very first letter is always capitalized. The second letter, if there's a second letter, is always lowercase. You would never write an elemental symbol with two capital letters, because if you see two capital letters, what that tells you is you've got two elements. But if I see two letters that are not capital, one of them's capitalized and the other one's not, that tells me that I've got one specific element. For instance, if I have C and O, and they're both capitalized, that means that I have carbon and oxygen. But if I CO and the first one is capitalized and the second one is lowercase, then what I have is cobalt, which is here. Cobalt, capital C, lowercase o. So it makes a difference how you write them. So for element symbols, the first one is always capitalized, the second one is not. From the periodic table, I also get the atomic number for an element. An atomic number tells me how many protons the element has. Now, protons gives an element its identity. No two elements have the same number of protons. If it has one proton, it's hydrogen. If it has two protons, it's helium. If it has three protons, it's lithium. If it has 48 protons, it's cadmium. No two elements have the same number of protons. That's what gives an element its identity. If, for instance, if I have nitrogen, nitrogen has 7 protons. I know that because its atomic number, which is this number that's in the top left-hand corner, is 7. It has 7 protons. If I added a proton to it, it is no longer nitrogen, it is now oxygen. Protons give an element its identity. That other number that's up there, the atomic mass, gives me essentially the average atomic mass of that particular element considering all of its isotopes. And we'll talk more about that as we move along. So let's move along to element, atom, compound. To start with, an atom is the smallest elemental unit that you can have. So every one of these squares in the periodic table represents one type of atom. So an atom is the smallest elemental unit. As long as you have an equal number of protons and electrons in that atom, then it is electrically neutral. Each of those atoms essentially represents an element. So each element that you see on the periodic table is a type of atom. Okay, it is a type of atom. It cannot be broken down into smaller pieces and still have that substance. If we have an atom of hydrogen, we have 1 proton, 1 electron, and no neutrons. If I start to take that apart, I no longer have hydrogen. I now just have its component parts, the protons and neutrons, protons and electrons. Normal hydrogen doesn't have any neutrons in it. So they cannot be broken down into anything simpler by chemical or physical means. You can break it down by nuclear means, but then you don't have that element anymore. There are 8 elements that make up about 99% of the Earth's surface: oxygen, silicon, aluminum, and iron. Oxygen is the most abundant element in Earth's crust. Now, what is a compound? A compound is atoms of 2 or more elements. Now, it doesn't necessarily even have to be 2 different elements. It could be 2 atoms of the same element making a compound. That would be a diatomic molecule. This can be taken apart by chemical means. They can be taken apart by chemical means into its simpler substances. For instance, if I have glucose, which is C6H12O6, this tells me that in this compound I have 6 molecules or 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. So if this were broken down, I could break this down into carbon, hydrogen, and oxygen. Okay, so I could break this down into the component elements by chemical means. Sodium chloride. Sodium chloride is another type of compound. It is an ionic compound, and it is made of sodium and chlorine. This also could be broken down by chemical means into its 2 component elements. So I have 2 or more elements coming together to make one substance. Now these are pure substances because I can't take them apart physically, but I can take them apart chemically, so they are referred to as compounds. They are made up of multiple elements. Molecules versus formula units. So the smallest particle that retains the characteristic chemical properties of a compound is one of its molecules. If it is a covalent compound like glucose, C6H12O6, then that is called a molecule. It is called a molecule because it is a distinct unit of that substance. Ionic compounds like sodium chloride are referred to as formula units because it's not a molecule necessarily. It is not a molecule. It is a compound, and this is a formula unit. But since ionic compounds form crystals where all of those are they're connected together based on the ratio of this formula right here, NaCl, it is not referred to as a molecule. So if it's molecules are covalent, formula units are ionic. And what makes a difference is whether they are covalently bonded, meaning that they are sharing electrons like this, or ionically bonded, which means that you have lost or gained electrons in order for these guys to literally stick together electronically. So if we take all of matter, we can separate it into 2 different types of things: pure substances and mixtures. Pure substances could be either compounds or elements. Compounds, which are things that are chemically combined, like water, sodium chloride, glucose, or any other sugars. Those are compounds. I can take them apart chemically, but I can't take them apart physically, so we still consider it a pure substance. Or the elements: hydrogen, helium, lithium, beryllium, etc. Those are elements. Those cannot be taken apart either. So those are pure substances. Mixtures, on the other hand, are not pure substances and can be taken apart by physical means, meaning that I can take them apart by filtration or some other physical method to get multiple pure substances. So I have two different kinds of mixtures over here, something called homogeneous mixtures and one called heterogeneous mixtures or heterogeneous mixtures or homogeneous, depending on how you want to pronounce that. Homogeneous mixtures are solutions and alloys. An alloy is simply a solution of metals. Think of this like when you dissolve sugar into water or Kool-Aid mix into water, you're making a solution. Okay, I can't filter that back out, but I can take it apart. If I take that solution and I distill it, or I fractionally distill it and pull off the water, I'm going to have the Kool-Aid and sugar mixture left in my original container and the water where the water condensed after the distillation. And so I've actually taken it apart into two different things. But I can't just filter it out if it's dissolved. Now, heterogeneous mixtures or heterogeneous mixtures like sand, dirt, etc. I mean, these are, as long as it's you've got a mixture of dirt, I could filter that into the smaller pieces and things like that. That's a heterogeneous mixture. You could think of this as like a bowl of beef stew where you've got beef and carrots and potatoes and such like that. And so you've got this mixture, and that can be taken apart, but I could physically pull out all the pieces of beef, physically pull out all the potatoes. That is a heterogeneous or heterogeneous mixture. So let's think about the parts of an atom. An atom is obviously a pure substance because every type of atom is an element, okay, or every element is a type of atom, and there are several different types of atoms of each one of the elements, and we'll talk more about that in a bit. The parts of an atom. Atoms are made up of protons, neutrons, and electrons. Protons are in the nucleus. They are relatively heavy compared to the electrons particularly, and they have a positive charge. So protons have a positive charge. Neutrons have about the same mass as a proton, but they have no electrical charge whatsoever. So neutrons have no electrical charge. But protons and neutrons are found inside the nucleus. Electrons are found outside the nucleus. Relative to protons and neutrons, electrons have negligible mass. Now that doesn't mean they don't have any mass. It just means that compared to protons and neutrons, they don't add any mass to the mass of an atom. Not appreciably. If I have a teaspoon of water and a swimming pool, obviously the teaspoon of water has mass, but if I put that teaspoon of water in the swimming pool, I haven't really appreciably increased the mass of the swimming pool. So electrons are like that. Electrons have a mass, but when you compare them to the mass of protons and neutrons, they don't really add any mass to the mass of an atom. They are located outside the nucleus. They have a charge that is equal to but opposite of that of a proton. So it has a -1 charge. Every electron has a -1 charge. And these things are located outside the nucleus in energy levels that when you put them together, they create what is called the electron cloud around the nucleus. So we have protons, neutrons, and electrons. Now there are subatomic particles that are smaller than these, but these are the major subatomic particles and the only ones that we're going to discuss in this course. As long as an atom has an equal number of protons and electrons, it is electrically neutral. So if I have a proton with +1 and an electron with -1, +1 minus 1 equals 0. So it's electrically neutral. If I have 2 protons, I'm going to need 2 electrons to make it electrically neutral. +2 minus 2 equals 0. So as long as I have an equal number of protons and electrons, my atom is electrically neutral. It has a 0 electrical charge. We've talked before about the fact that if you remember the very first lecture about the nature of science, that science is not static, okay? Our view of atoms has changed significantly through the centuries. In 1803, Dalton, who was a scientist, saw an atom being a solid sphere. He didn't know anything about subatomic particles. He was unable to determine that there were subatomic particles. He just thought there was each atom was a solid sphere. Then moving forward, J.J. Thomson saw an atom as being a sphere, but it had little negative particles all through it because he had discovered electrons. So he was able to discover electrons. So he knew that he had these negative particles that were inside what would be like think of a blueberry muffin. So you have this muffin, which collectively is electrically neutral, but I have all these little blueberries in here which have a negative charge, which meant that the muffin part had to be positively charged in order to cancel that out. But he knew that there were these little particles that were negative throughout the atom, but he still saw it as a solid piece, blueberry muffin, and inside the blueberry muffin all the little blueberries had a negative charge, and we call that plum pudding. And plum pudding because of the fact that he was British, and plum pudding was a type of dessert where you had the cake with plums all through it, and so that's why it was called the plum pudding model. Rutherford created what would refer to sort of as the planetary model. He saw that he discovered that there was a nucleus. He discovered that there was a nucleus that had a positive charge. And so you have this nucleus that's positively charged, and then you have all of these electrons that are around it that are negatively charged. So collectively they form this neutral substance because you've got this small nucleus in the middle, and there's a whole series of experiments that Rutherford did that involved gold foil and bouncing neutrons off of something and off the center of the atom and whatnot that allowed him to discover the presence of a nucleus. But what I need for us to know right now is that he discovered that there was a nucleus and that you have all of these negative electrons around it. Then Niels Bohr in 1913 said that each one of these electrons